hybridization in this video will help you to finish up the Vesper theory assignment that you have that we started with video 3. So next we need to talk about hybrid orbitals. Vesper theory works well when accounting for molecular shapes, but it doesn't help very much when describing the types of bonds formed. The orbital hybridization provides information about the molecular bonding and the molecular shape. So in hybridization, several atomic orbitals mix to form the same total number of equivalent hybrid orbitals. So we have some numbers to help us. Because we have sp and d orbitals overlapping to create these molecular orbital bonding, the hybridization uses their quantum numbers to help denote the overlaps. So the types of overlaps, we have S, sp, sp2, sp3, dsp3, and d2 sp3. So, fill those in the table. Then, what this means is, when we have something bonded, no matter the total number of things that are bonded or unshared pairs on there, the groups that are coming off the central atom, then we're going to be able to assign the hybridization overlaps, which these are on your handout page. Okay, so the S is when you just have one bond, so that's between two elements. Okay, then when you have sp on down, that's when you have things connected to a central atom, so you have more than two atoms in your structure. So this has two groups coming off for sp, sp2, 3 groups, sp3 is 4 groups, so on down. So then dsp3 is 5 groups, and d2 sp3 is 6 groups. In just a second, we're going to draw some Lewis structures so you can count the hybridization. But it's total things coming off the central. And if you look, counting up with the exponents how many total letters would be in this notation, that is one way that will help you to figure out the hybridization. So sp has 2 letters, so that's why there's 2 groups. sp2, this is really spp, right? Because p squared just means there's double p. So that's a total of 3 letters, so that's why there's 3 groups. When we go down to dsp3, we have a d, we have an s, and we have 3 p's. So that is 5 letters total in the notation, so that has 5 groups coming off. On our handout that we got with our Vesper theory handout, remember how I said before, skip the electron paired geometry section? That's the hybridization notation. So it just kind of goes along horizontally. So if you are picking the name of something in that row, then you can just look in this electron paired geometry column to figure out what the hybridization is. Okay? So, for example, if you say that something is tetrahedral, is the shape in the name because it's a 4, 0, that's 4 total groups coming off, so we're going to call that sp3. Okay? So this sheet has all the answers for you. You just have to know how to use it. Okay? So let's try it out. So how to determine our hybridization? We're going to count the number of atoms and unshared pairs that are bonded to the central atom of a molecule. So we have to draw the Lewis structure first. So we have PCl3. Phosphorus is going to be our central, and phosphorus has and phosphorus has 5 valence electrons. This is a tight squeeze, sorry. And then chlorine, we have 3 of them, and each chlorine has 7 dots. And there's the connection. There's the second one. And the third. Okay. So now we can think about it the same way as we were identifying the name. So let's go about it that way. So on the P, on our central atom, how many atoms are connected to it? We have 1, 2, 3 atoms connected, and how many unshared pairs? 2 electrons makes 1 unshared pair. So if we were looking at our handout, we would say a 3-1 is going to be a trigonal pyramidal, right? But that's not really the hybridization. The hybridization would be the sp from the electron pair geometry column in that same row. So since it's 3-1, that is equal to a total of 4 groups coming off the central, so we would call that sp3. If you just want to look at the column and label it from there, that is okay. If you have something, in our next example, we have where we don't have a central atom, then we just use one of the atoms that's most centrally located. So these are the tricky ones where you have 2 carbons and then other stuff that you have to bond to the carbons. So we're going to put the carbons in the center, and each carbon has 4 dots. And then I have 2 hydrogens, so we're going to just evenly distribute those. So I'm going to put 1 hydrogen paired up with the left carbon, and 1 hydrogen paired up with the right carbon. Okay, so we know that we're going to connect the carbons once. We are actually going to have to connect the carbons a total of 3 times, make a triple bond there. Okay, so looking at our carbon, we just pick one of the centrally located in the molecule, so that's one of the carbons, and the carbons are identical because it's symmetrical if we cut it in half, so I'm just picking the left one. So when we pick the left one, we look at the groups that are coming off of it. How many things are connected to it, whether they're unshared pairs or groups of other connected atoms. So here's one group, the hydrogen's connected, and then everything else from the other carbon on is another group. So that would be 2 connections, 2 groups. So looking up at the table, when you have 2 groups, that is equal to sp. It's a little bit more difficult to figure out when you don't have a central atom, but you can still do it. I believe in you. Okay? So this is how you're going to figure out the hybridization that corresponds to the 7 that you drew the Lewis structure and identified the molecular shape on the Vesper theory assignment. Okay? So if you would like to pause now and get those done real quick, and then we're moving on to polarity to finish up the assignment. As mentioned before, covalent bonds share electrons between the atoms. That's what we're all about, sharing is caring. The bonding pairs of electrons can be pulled like in a tug of war between the nuclei of atoms sharing the electrons. So because of this tug of war, we have what are called polar bonds or nonpolar bonds, where the covalent bond is shared unequally in a polar covalent bond, and a nonpolar covalent bond is when the electrons are shared equally. And we can identify these polar versus nonpolar when we draw a Lewis structure. So what does nonpolar look like? It's very symmetrical. So if you need to write a little note to yourself that it's symmetrical, go for it. Okay? But I'll just draw so you can see. So we have CH4. Carbon is going to be our central atom. Carbon has 4 dots. We need to connect 4 hydrogens to it, and each hydrogen has 1 dot. And there we go, we're done. The carbon has an offset completed. So this is nonpolar because the hydrogens are evenly distributed, they're evenly pulling on each other, and this would be a 4, 0 called a tetrahedral. If you want to look at that picture on your handout, that kind of shows you that it is very symmetrically spaced out. Okay, because sometimes we don't draw it so spaced out. So that would be nonpolar because every electron is paired up, evenly distributed, nonpolar, everybody's happy. C2H4. We're going to put our carbons in the center. I already know we're going to connect them once, so at least, so I'm going to go ahead and connect them. Then we have 4 hydrogens to evenly distribute, so 2 on a side, or 2 connected to each hydrogen, the carbon. again, we have those dots left over on the carbon, so we're going to create a double bond. Here again, it doesn't draw perfectly, but for each carbon, we have 2 hydrogens plus a double bond on both sides. That is a symmetrical structure. PCl5. Phosphorus has 5 dots. Okay, and we have 5 chlorines to connect, and each chlorine starts out with 7 dots. So each chlorine will be connected to a dot from the phosphorus. Alright, a lot of people don't realize that this one can be nonpolar, but it is, because this is a 5-0, so we would call it trigonal bipyramidal if we looked at our handout. Okay, but if you look at the handout, it shows you that it has 2 planes, so it has a vertical in line, and then it has the other 3 spread out evenly distributed. So nonpolar is symmetrical, even everything's paired up on the central atom. Okay, another hint at describing what nonpolar looks like is usually there are no unshared pairs on the central. Atom, on the central atom. So that usually follows, but there are a few cases when that would not work. Okay, so that's what nonpolar looks like, very symmetrical. Polar then is very unsymmetrical. Okay, when we have polar bonds, we actually have what are called slight charges too, or partial charges. The more electronegative atoms attract the electrons, so then they gain a slightly negative charge. The less electronegative atoms have then a slightly positive charge because the electrons are not as close to them. So to denote this, we use the Greek letter delta with our charges. It kind of looks like an S on your notes on here. Mine looks like a curly Q D, so we'll see that in a second. So what does polar look like? Well, we have water. If we have water, and we have hydrogen with a hydrogen, okay, we have unshared pairs in the oxygen, okay? Because of the unshared pairs in the oxygen, that's what makes it uneven, right? So the unshared pairs are different than the hydrogen atoms. If it was all 4 hydrogens connected, there'd be a different story, okay? So this is polar because of the unshared pairs on the oxygen. And because the oxygen has those extra unshared pairs, then we say it has a slightly negative charge. So there's my delta, and then you put a little negative sign for the charge. If the oxygen is slightly negative, then each of the hydrogen gets its own slightly positive charge. Okay, so that would be a polar molecule. Next, we have HF. So this one does not have a central, but F's have 7 electrons, and hydrogens have 1, so I connect it. It doesn't have a central, so we couldn't come up with the molecular geometry name, but we do know that it's polar because all of the electrons are on one side. All of the electrons are on the fluorine. So that means that the fluorine is slightly negative, and the hydrogen is slightly positive. Hydrogens will usually be slightly positive. Okay. Last one, NH3. Nitrogen has 5. And we have 3 hydrogens to connect. Okay. So our slightly positives are the hydrogens because they have 0 unshared pairs around them. And then the nitrogen has an unshared pair. So then that would be its slightly negative. Okay, so when you have a polar molecule, you usually show that it's polar by showing these slightly negative, slightly positive charges. The negative side is the side with more electrons. So there could be a case where you have a bunch of chlorines on the outside that have tons of unshared pairs around them, And so then that would then in fact be the slightly negative side. Okay? Last but not least, we can describe our polar covalent molecules where we have something called a dipole, where one end is slightly negative, one end is slightly positive. And because we have these two differences, we call that a dipole. So, with this information, you should be able to finish the Vesper Theory handout. You should be able to turn it in today. Please make sure that you draw the slight structures and label polar, nonpolar for that last section. If you have questions, check out the answers.